Welcome back students. I am Dr. Rajesh Singh and this is part 2 of the exercise 5.1 from the book Bartle and Sherbert. In this video we will solve question number 4 onwards. So let us start with question number 4. So in question number 4 we are given the greatest integer function and we have to determine points of continuity for each of the following 4 functions. So in the first case, that is part A, we are given fx equal to greatest integer function x for all x belonging to R. So we have to determine its points of continuity. So we claim f is continuous at all real values except at integers. So that is f is continuous on R minus z. So this is what we are going to prove. So let C belonging to R be any real number. So we have picked any real number. We will show that if C is an integer, then f is discontinuous at C, and if C is not an integer, then f is continuous at C. So we will do this in two cases. So case 1, C is an integer. So in this case, we will take a sequence that converges to C, but the corresponding sequence fxn will not converge to C, and hence we will be able to conclude that f is discontinuous at C. So consider the sequence. Let xn is equal to C plus minus 1 to the power n upon n for all n belonging to n. So clearly xn converges to C. The way we have constructed the sequence xn, it converges to C. Now what about f of xn? So if it is easy to see that f of xn is equal to C minus 1 if n is odd, and it is C if n is even. So f of xn is an oscillating sequence and hence is not convergent. So it can be easily seen that f of xn oscillates between C minus 1 and C. So it is not a convergent sequence in R. It is not convergent. So by discontinuity criteria, f is not continuous at C. So by discontinuous criteria, f is not continuous at C. So in this case, we have shown that if C is an integer, then f is not continuous at C. Now case 2, C does not belongs to Z, that is C is not an integer. So in this case, we will show that f is continuous at C. So for that, take any arbitrary epsilon greater than 0. So let epsilon greater than 0 be any real number. So we have picked any arbitrary epsilon. Now we will show that there exists a delta greater than 0 such that x minus c less than delta will imply fx minus fc less than epsilon. So now c is not an integer. So if c is this, then this is c plus 1 and this is c. So these two are consecutive integers between which the number c lies. So I will construct so I want my interval to be like this. This should be my c minus delta and c plus delta. So for this delta, I have to take the delta equal to, so let delta equal to minimum of, so what I will take, half of this distance, which is c minus mod c by 2, and half of this distance. So this is how I will choose my delta. So delta equal to minimum of c minus mod c by 2 and c plus 1 minus c by 2. So by this choice of delta, all my x lies between this interval, so it does not take any integral values. So that is my aim. So then clearly x minus c less than delta implies fx is equal to greatest integer value of c, because all x lies in this interval, and they, if you take the greatest integer function of all real values lying in c minus delta to c plus delta, the value will be the greatest integer function of c. So this implies fx is constant on x on the interval c minus delta to c plus delta. So this implies fx is equal to fc, and this implies fx minus fc is equal to 0, and which is clearly less than epsilon. Hence, for delta equal to minimum of c minus c by 2 and c plus 1 minus c by 2, x minus c less than delta implies fx minus fc is less than epsilon. Hence, f is continuous at c. So from case 1 and 2, we conclude that f is continuous at c if and only if c belongs to r minus z. So now this completes part A of question number 4. Now we will take part B of question number 4. So in part B, we are given gx equal to x, greatest integer function of x. So B part, gx is equal to x, greatest integer function of x for all x belonging to R. So this is what we are given. So again, in this case, we claim that G is continuous on R minus Z union 0. So we will show that G is continuous at all real values including 0 except integers. So except at non-zero integers, G is continuous everywhere. So this is what we are going to show. So for this, again, we will take any real number, any arbitrary. So let C belonging to R be any arbitrary real number. So now case 1, so this we will do this in 3 cases. Case 1, when C is equal to 0. Case 2, when C is an integer, non-zero integer, and case 3, when C is a non-integer. So case 1, when C is equal to 0. So in this case, we will show that G is continuous. So for that, we will take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have to show that G is continuous. So for this, now if you can see, this is 0, this is 1, and this is minus 1. So what I want only 0 to be in my interval c minus delta to c plus delta. So I want to choose a delta such that only 0 is the integral value in the interval c minus delta to c plus delta. So for that, what delta we should take? We should take delta equal to, this should be minus 1 by 2 and 1 by 2. So the delta equal to 1 by 2 will work. So first we will take a bound on delta. So let x minus 0 is less than 1 by 2. So this is the bound we are taking. Then consider gx minus g0. So this is equal to x minus 0. So this is equal to and this is what is the value? This is 0 if because if x is greater than 0 and x lies between 0 to 1 by 2, so greatest integer function of x will be 0, so this will be 0 if x is greater than 0. And this is equal to mod x if x is less than 0. So both the things are less than equal to definitely mod x. So and this is equal to mod x minus 0. So what delta we should take? We want this to be less than epsilon. So this should be less than epsilon. So for that we should take delta equal to, so let delta equal to minimum of 1 by 2 and epsilon. Then clearly x minus 0 less than delta implies gx minus g0 is less than epsilon. Hence g is continuous at c equal to 0. So we have shown that if I take c equal to 0, then g is continuous at c. Now we shall take next case when c is not an integer and c is not equal to 0. So case 2, c belongs to r minus z. Okay. So we will show that in this case f is continuous. So for that again take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have to find a delta greater than 0 such that x minus c less than delta should imply gx minus gc less than epsilon. So what shall we do? We shall take let delta 1 equal to minimum of c minus mod c by 2 and c plus 1 minus c by 2, same as we did in the last part. So because c is a real number which is not an integer, so the consecutive integers between which c lies are these two. So we want to create an interval which is around c and which does not contain these 2 points. So for that we can take delta 1 equal to this. So for this choice of delta, this property will be satisfied. Okay, so I have taken delta 1 to be equal to minimum of c minus mod c by greatest integer function of c by 2 and greatest integer function of c plus 1 minus c by 2. So now for x minus c less than delta 1, so I am taking a bound using delta 1 because my delta will be different from this delta 1. There will be another condition. So for now I am taking this bound, like in the previous case I took the bound of 1 by 2. So in this case I am taking the bound of delta 1. So for x minus c less than delta 1, consider gx minus gc. So this is equal to x minus c greatest integer function of c. So because my x lies in this, so the greatest integer function of x will be mod c. So this is equal to x c minus c times greatest integer function of c. So I can take this x minus c and this is mod c. So this can be negative or positive, so I have taken the mod here. So I want this to be less than epsilon. So what delta we should take? We should take delta, let delta equal to minimum of epsilon by mod c. So this can be 0 also, so I have to, so what we have to take, we have to add +1 to it so that it does not create any problem, and then we can take delta 1 here. So delta is less than delta 1, so this bound is satisfied, and delta is also less than epsilon by mod c +1. So then clearly for the above choice of delta, x minus c less than delta implies gx minus gc is less than epsilon. Hence g is continuous at c. So we have shown that in this case g is continuous. So we are left with the last case when c is an integer and c is not equal to 0. So case 3, c belongs to z and c is not equal to 0. So in this case we will show that the function is discontinuous. So for that we will construct two sequences xn and yn such that both converges to c, but their corresponding sequences converges to different limits. So let xn equal to c minus 1 by n and yn equal to c plus 1 by n for all n belonging to n. So then clearly xn converges to c and yn also converges to c. So we have got two sequences that converges to c. Now what about the corresponding sequences gxn? So let now g of xn is equal to g of c minus 1 by n. So this is equal to c minus 1 by n, greatest integer function of c minus 1 by n. But now c is an integer, so c minus 1 is a number smaller than c, so its greatest integer value will be c minus 1. So this is true for all n belonging. So for all n belonging to n, gxn is equal to c minus 1 by n into c minus 1. So clearly gxn converges to c into c minus 1. Now for all n belonging to n, g of yn, so this is g of yn is g of c plus 1 by n. So as before it is c plus 1 by n and greatest integer of c plus 1 by n. So this is c plus 1 by n times c. So clearly g of yn converges to c square. So since c is not equal to 0, so c square is not equal to c times c minus 1. Hence the two sequences gxn and gyn converges to different limits. So the two sequences converges to different limits. So by discontinuity criteria, g is not continuous at c. So hence from the three cases we conclude that g is continuous at c if and only if c belongs to r minus z union 0. So this completes part B of question number 4. Now let us take part C of question number 4. So in part C we are given the function hx, which is greatest integral value of sin x. So in part C, we are given that hx is equal to greatest integer value of sin x for all x belonging to R. So if we take gx equal to mod x and fx equal to sin x for all x belonging to R, then h is equal to GOF. So h is the composition of these two functions. H is the composition of GOF. Now f is continuous everywhere, so this will not, so f will not create any problem in the continuity of h. So h can be discontinuous only at the points where g is discontinuous. If g is continuous at a point c, then h should be continuous, because composition of two continuous function is continuous. So we have to check at the points where g is discontinuous. Now from part A, we know that g is continuous on R minus z. So since composition of two continuous function is continuous, since composition of two continuous function is continuous and g is continuous on R minus z, so h equal to GOF is continuous at all real values except when sin x is an integral value, that is sin x becomes integer. So only at those real values the function may be discontinuous, otherwise the function GOF is continuous everywhere. So now we have to find points at which values for which sin x is integral. So we know that sin x takes only three integral values, that is -1, 0 and 1. So only these three integral values sin x takes. So we have to find points at which sin x is equal to 0, points at which sin x equal to -1, points at which sin x equal to 1. Now sin x is equal to 0 if x is equal to n pi and n belongs to z. Sin x is equal to 1 if x is equal to 4n plus 1 pi by 2, and n is an integer, and sin x is equal to -1 if x is equal to 4n plus 3 pi by 2, n is any integer. So this is the solution set for the equation sin x equal to 0, sin x equal to 1, sin x equal to -1. So let S1 is equal to n pi n belonging to z, S2 is equal to 4n plus 1 pi by 2 n belonging to z, and S3 is equal to 4n plus 3 pi by 2 if n belongs to z. If n belongs to z, so S1 is the solution set for the equation sin x equal to 0, S2 is the solution set for the equation sin x equal to 1, and S3 is the solution set for the equation sin x equal to -1. So now we will claim that. So our claim will be, this is what we are going to show. Claim H is continuous at C if and only if C belongs to R minus S1 union S2. So that is, we are going to show that H is continuous at S3, but H is not continuous at S1 and H is not continuous at S2. So this is what we are going to show. So this we will discuss in 4 cases. So case 1, when C belongs to R minus S1 union S2 union S3. So that implies that sin C is not an integral value, and since sin C is not an integral value, so GOF is continuous at. So in this case f of C does not belongs to Z, because sin C is not an integral value, because we have S1 S2 S3 are the solution set for the integral values. So because C does not belongs to S1, neither it belongs to S2 nor it belongs to S3, so sin C is not an integral value. So then G is continuous at FC, hence GOF is continuous at C, being the composition of two continuous functions. So that is, H is continuous at C. So we have shown that in case C belongs to R minus S1 union S2 union S3, then H is continuous at C. Now case 2, when C belongs to S3. So again we will show that in this case H is continuous. So let epsilon greater than 0 be any real number. So we are taking any arbitrary real number. So we have to find delta such that x minus c less than delta implies hx minus hc less than epsilon. So C is here, C is not in S3, or C belongs to S3. So C is of the form, C is equal to 4k plus 3 pi by 2 for some k. So the next value will be, so if I will add pi by 2 here, then what I will get, if I will add pi by 2, then it will be 2k plus 2 pi this is 2k plus 2 pi, and if I will subtract pi by 2, then it will be 2k plus 1 pi, and this is C. So this distance is pi by 2 and this distance is pi by 2. So this one, because this is on the right of 4k plus 3 pi by 2, so this is fourth quadrant and this is third quadrant. So sin x in this case is negative and sin x in this case is also negative. So in both the cases we get negative value. So what we will take, let delta equal to pi by 4. So I am taking delta equal to half of this distance. This is pi by 2, so I am taking half of this distance. So my x will lie in third or fourth quadrant. For x minus c less than delta, that is x minus c less than pi by 4, consider hx minus hc. So this is equal to sin x minus sin c. So sin x, because x lies in either in third quadrant or fourth quadrant, Because of the choice of delta, so sin x is some negative value and its greatest integer value will be -1, and c is equal to 4k plus 3 pi by 2, which is obviously -1. So this is equal to 0, which is trivially less than epsilon. So clearly for delta equal to pi by 4, so x minus c less than delta implies hx minus hc is less than epsilon. Hence h is continuous at c. So in this case we have shown that h is continuous at c. So for taking delta equal to pi by 4, this works because our x in that case will lie in either third quadrant or fourth quadrant. So the value of sin x will be a negative number, and if I take the greatest integral value of that number, it will be -1. So this is what we have got if we have taken c in S3. Now we will take c in S1 and we will show that it is discontinuous. So case 3, when c belongs to S1. So in this case, that is c is equal to k pi for some k belonging to z. So this is k pi. So next is 2k plus 1 pi by 2. So adding, if I will add pi by 2 in this, so this is pi by 2 distance, and again if I will subtract pi by 2, then I will get 2k minus 1 pi by 2. If k is even, then this will be first quadrant, and if k, this interval will be first quadrant, and if k is odd, then this interval will be third quadrant. So in this case I will take a sequence that converges to c, but the corresponding sequence does not converge to c. So let xn is equal to c plus 1 by n. So depending on whether k is even or odd, it will be either 0 or -1. Then h of xn is equal to, which is sine of xn, which is equal to sine of c plus 1 by n. So c plus 1 by n either lies in the first quadrant or third quadrant. So which is equal to 0 if k is even, because in case of even it is first quadrant, so positive sign, so it will be 0, or it is -1 if k is odd, because in case of odd it lies in the third quadrant. So h of xn converges to 0 if k is even, and h of xn converges to -1 if k is odd. Now we will take another sequence. So let yn is equal to c minus 1 by n. Then yn will belong to this interval, and if k is even, then this is fourth quadrant, so negative, so it will be -1, and if k is odd, then it will be second quadrant, so positive. Then h of yn will be equal to -1 if k is even and 0 if k is odd. So limit n tends to infinity, h of yn is equal to -1 if k is even and 0 if k is odd. So in case of even, h of xn is converging to 0 while h of yn is converging to -1, while in case of odd, h of xn is converging to -1 and h of yn is converging to 0. So in either case, the sequences h of xn and h of yn are converging to different limits. So thus we are able to construct two sequences xn and yn in R such that xn converges to C, yn converges to C, but their corresponding sequences h of xn and h of yn converges to different limits. Hence, by discontinuity criteria, h is not continuous at C. So this completes case 3. Now we are left with the last case, which is case 4 when C belongs to S3. So case 4 when C belongs to S3, that is C is of the form 4k plus 1 pi by 2 for some k belonging to Z. So again in this case we will construct a sequence that will converge to C, but the corresponding sequence will not converge to HC. So now this is our C, which is equal to 4k plus 1 pi by 2, and if I will add pi by 2 to this, so what I will get 4k plus 2 pi by 2, which will be 2k plus 1 pi, so which is odd. So this is second quadrant. So this is second quadrant. So any number lying in this will give a positive value for sine. So I will take sequence, let xn equal to C plus 1 by n, then xn belongs to this. So sine of h of xn, which is equal to sine of xn, which is equal to sine of C plus 1 by n, is equal to 0 for all n belonging to n. So h of xn is equal to 0 for all n belong to n. So clearly h of xn converges to 0, which is not equal to hc, because hc is equal to 1, because since hc is equal to sin c and sin c is 1, so this is equal to 1. The sequence xn converges to C, but h of xn does not converge to hc, hence h is not continuous at C. So hence from all the possible cases we conclude that h is continuous at C if and only if C belongs to R minus S1 union S2. Sorry, this was the case when C belongs to S2. Okay, so case 4 is when C belongs to S2. So C is of the form 4k plus 1 pi by 2. So we are able to show that H is continuous at C if and only if C belongs to R minus S1 union S2. So this completes part C of question number 4. Now let us take part D. So in part D we are given the function k, which is greatest integral value of 1 by x. So let us start with part D. So we are given the function kx equal to greatest integral value of 1 by x for all x not equal to 0. So let s equal to 1 by n, n belonging to z. So we will show that if C belongs to R minus S, then Fk is continuous at C. So claim, because this will take integral values only when x belongs to this set 1 by n. If x is of the form 1 by n, then this will take the integral values, and we know that this will be discontinuous whenever this takes the integral values. So claim k is continuous at C if and only if C belongs to R star minus S, where R star is equal to R minus 0. So because this is not defined at 0, so we are removing the point 0. So let C belong to R star be any point. So we shall consider the first case when C does not belongs to S. So in this case, we will show that k is continuous at C. So let fx equal to 1 by x for all x not equal to 0. Then f is continuous at C and fc is not an integer. Fc is not an integer. So the function gx equal to mod x, greatest integral value of x, is continuous at fc. So since composition of two continuous function is continuous, so k equal to gof is continuous at C. So this completes case 1. Now let us take the case 2. Case 2 when C belongs to S, that is C is equal to 1 by M for some M belonging to Z. So this is our C, which is equal to 1 by M. Then this is 1 by M minus 1, and this will be 1 by M plus 1. So what we will do, since 1 by M is a limit point of both the sets 1 by M plus 1 to 1 by M, because this is an interval, so boundary points are also limit points, and 1 by M to 1 by M minus 1. So C is a limit point of this set of this interval also, and C is a limit point of this interval also. So there will be sequences xn in this that converges to C, and sequence yn in this that converges to C. So there exist sequences xn in 1 by M plus 1 to 1 by M, and sequence yn in 1 by M to 1 by M minus 1, such that xn converges to C and yn converges to C. Now for n belonging to n, k of xn is equal to 1 by xn, and what this value will be? This value will be equal to m, because 1 by m plus 1 is less than xn is less than 1 by m, so that is m plus 1 is greater than xn is greater than m. So these are two consecutive integers and xn lies between them. So greatest integral value of xn will be the smallest integer, which is m. So k of xn is equal to m for all n belonging to n. So clearly k of xn converges to m. Now for n belonging to n, k of yn is equal to is equal to 1 by yn, and which is equal to the smaller of the two integer m minus 1 and m, so this is m minus 1. So k of yn converges to m minus 1. Now we have got two sequences xn and yn both converging to C, but their corresponding sequences kxn and kyn converging to different limits. Hence k is discontinuous at C. Thus, from the two possible cases, we conclude that kx equal to 1 by x is continuous on r star minus s, where s is the real numbers of the form 1 by n, where n belongs to z. So this completes question number 4. So in this video I will solve till here. In the next video I will proceed from question number 5 onwards. Till then, stay tuned and subscribe to our YouTube channel. Thank you.